Welcome to module 19. This is on the course on pericyclic reaction and organic photochemistry. We'll continue with the sigmatropic rearrangement in this module. We have some portions left which are the aromatic Claisen rearrangement and asymmetric Claisen rearrangement in the portions of sigmatropic rearrangement. Now an aromatic Claisen rearrangement is nothing but the allyl ether of phenol undergoing a rearrangement to give orthoallyl phenol as the product. This is a thermal rearrangement. This is a 3,3 sigmatropic rearrangement. If you consider this carbon-oxygen bond to be broken, then it is 1, 2, 3, 1, 2, 3. So the ortho position of the phenolic group and the terminal position of the allyl group are joined together in a C-C bond forming reaction, forming an intermediate which is this ketone. The intermediate is ketone does not survive under the reaction condition. It readily undergoes ketoenol tautomerism to give the corresponding phenolic product, which is orthoallyl phenol in this particular case. When the ortho positions are blocked by methyl group or some substituent groups that are present in the ortho position, in the 2,6 position for example, this could be simply 2,6 dimethyl phenyl allyl ether. Initially it undergoes the Claisen rearrangement to give the ortho-allyl substituted derivative. Since there is no hydrogen here, this cannot undergo the ketoenol tautomerism to the corresponding phenol. However, it can undergo further cope rearrangement under the reaction condition to the para position. In other words, the allyl group is shifted to the para position, and from the para position, of course, you have a hydrogen which can undergo ketoenol tautomerism to give the para allyl substituted phenol. Suppose if there is no hydrogen in the para position also, then the dienone systems that are formed are isolated as the product. Claisen rearrangement, the aromatic Claisen rearrangement normally take place in the temperature range of 200 to 250 Celsius. Now, in the case of the 3,5 dimethyl phenyl allyl ether case, for example, the initial Claisen rearrangement gives the ortho-allyl derivative. You can see here, this is a carbon that is connected to the ortho position with the methyl substituent, and that methyl substituent appears here. Subsequently, further reaction leads to it depends on the temperature as well as the solvent polarity in this particular case. So the rearrangement essentially can proceed either through a 3,3 sigmatropic rearrangement or a 3,5 sigmatropic kind of a rearrangement, which forms the para substituted product in this particular case. In decalin they are formed in nearly equal amount, whereas in DMF the 3,3 sigmatropic rearrangement product is the major product that is formed under the reaction condition. Now, instead of an allyl derivative, if you take a propargyl derivative, the propargyl derivative also undergoes the Claisen rearrangement. In other words, this is phenyl propargyl ether is what is undergoing the Claisen rearrangement. Initial rearrangement essentially gives you this ortho allynyl derivative. This is an allyne derivative. The ortho allynyl derivative undergoes the ketoenol tautomerism to give the phenyl allyne kind of a orthohydroxy phenyl allyne derivative is what is formed in this particular case. This does not survive the reaction condition. It undergoes hydrogen transfer. In other words, this is a 1,5 hydrogen shift is what is taking place to generate the intermediate which is shown here, for example. This intermediate essentially undergoes cyclization to give this chromine derivative, which is the final product of the propargyl phenyl ether rearrangement. So this is one convenient way to synthesize the chromine derivatives of several kinds. Suppose if we take the bis phenyl propargyl derivative of this kind, when it is heated in diethyl aniline as the solvent, which is a high boiling solvent, the chromine derivative is initially formed. The chromine derivative is further set up for a 3,3 sigmatropic rearrangement in this particular instance. This is essentially undergoing a 3,3 sigmatropic rearrangement to give this particular product. This product is now undergoing an is undergoing an addition of a hydroxy functional group across this double bond in a Markovnikov fashion to give the benzopyran, benzofuran fused system of this kind. So it's an elegant way of synthesizing a fairly complex heterocyclic, benzanulated heterocyclic derivative of this kind. Now, the asymmetric Claisen rearrangement examples are shown here. Remember, in the case of Claisen rearrangement, if you have a substituent in the alpha position or in the substituent in the double bond, it will create a chiral center. And the reaction is again proceeding through a 6-member cyclic transition state, so there should be a high stereoselectivity for this reaction. When the pure R isomer, which is corresponding to this R isomer here, configuration here, with the E isomer of the double bond is taken and heated to 200 degrees. The product formed are these two products. The major product formed is the S configurated isomer with the E as the stereochemistry of the vinyl group that is being present here. The R substituted isomer has the Z stereochemistry. This can be explained again by the 6-membered cyclic transition state. The reaction yield is not that great, it's only about 50%, but the diastereoselectivity is very good in this case. 82% of the SE isomer and 18% of the RZ isomer is what is formed from the RE isomer of the corresponding starting material. Now this is an experiment probably that was done in an NMR tube. You can see here CdCl3 is used as a solvent, which is a typical NMR solvent. Europium FOD3 is a shift reagent. This is essentially acting as a Lewis acidic reagent in this particular case. So catalytic amount of europium FOD3. FOD is a ligand which is a beta diketonide ligand is attached to the europium center. So it's a beta diketonide salt of the europium, which is a Lewis acid because europium is in the 3+ oxidation state. So it probably coordinates with the oxygen and accelerates the reaction. The reaction is essentially, this is a phenyl allyl ether. So the carbon-carbon bond formation takes place between this carbon, which is orthocarbon, to this particular carbon, which is the allylic terminal carbon of the allylic system. In the process, you can see here this well-defined stereochemistry of the starting material, resulting in the formation of a very well-defined stereochemistry of only one enantiomer. The reaction yield is about 79%. The enantioselectivity is about 97% corresponding to this particular configuration, which can be explained on the basis of a 3,3 sigmatropic rearrangement involving a suprafacial migration of the carbon over here to generate the new chiral center at this particular position. Now here the boron reagent is used as a Lewis acid, specifically 1.5 equivalent of this Lewis acidic compound is used. You can see here the Lewis acid is a chiral Lewis acid, so it is actually a chiral Lewis acid catalyzed reaction. This probably forms initially a boronate ester using this particular phenolic ester, in this particular free phenolic OH is what is generated here. The rearrangement takes place at this carbon, which is the orthocarbon, because the other orthocarbon is occupied by the hydroxy functional group. So chirality induction takes place. Up to 94% enantioselectivity of the S isomer is formed from the E isomer of the allyl derivative in this particular case, because of the chiral nature of the catalyst that is being used. It is really not a catalyst, it is used in stoichiometric amount to form the corresponding boron phenolate of this kind in this particular instance. And the rearrangement is essentially breaking of this carbon oxygen bond. This is 1, 2, 3 and 1, 2, 3 in the ortho position. On the other side, the free ortho position is what is undergoing the 3,3 sigmatropic rearrangement in this particular instance. So what we have seen here is the aromatic Claisen rearrangement asymmetric versions. The first instance, this is a first generation asymmetric induction because this is a chiral substrate is what is undergoing the rearrangement. The second case, a chiral catalyst is used. In the third case, more or less a chiral auxiliary is what is used. So there are 3 different kinds of examples are shown for the asymmetric induction during the course of the aromatic Claisen rearrangement. There are not that many examples of aromatic Claisen rearrangement. However, there are several examples of aliphatic Claisen rearrangement, which are asymmetric aliphatic Claisen rearrangement that is taking place. These are the favorable situation for the high enantioselectivity or high diastereoselectivity, as the case may be, observed for the asymmetric Claisen rearrangement. First of all, the reaction has a very high preference to chair like a transition state. It's a very well defined transition state, and well defined double bond stereochemistry in the starting material also helps in the stereoselectivity of this reaction. The stereochemistry is often predictable because of the fact that you have a chair type of a transition state with a very well defined double bond stereochemistry. Therefore, the high diastereoselectivity and enantioselectivity observed in the aliphatic asymmetric Claisen rearrangement is not a very surprising factor in view of the following points which are favorable towards the high enantio and diastereoselectivity of these reactions. This is an example that is reported by E.J. Corey. This particular boron derivative is used as a reagent in this particular case. It is actually used as a catalyst in this particular case. This is a chiral Lewis acid catalyst is what is used. This particular configuration of the chiral Lewis acid, when treated with this particular ester, which is a allyl ester, the allyl ester is enolized in the alpha position with the 2 different base, isopropyl diisopropyl ethylamine or triethylamine as a base. Depending upon the kind of reagent, the base that is used, the two different diastereoisomers are produced. In the case of diisopropylamine, ethylamine, which is a bulky base, the boron reagent generates the corresponding E-boron enolate, which is this particular ketene silyl acetal kind of a boron enolate is what is formed, whereas triethylamine base gives you the Z type of a stereochemistry of this. So what we have here is a EE isomer of the boron enolate, and in this particular case the EZ isomer of the boron enolate is what is formed. So diastereoselective 3,3 sigmatropic rearrangement produces the corresponding gamma delta unsaturated carboxylic acid in this particular case. This is very similar to a Ireland Claisen type of a rearrangement, except that it is a boron enolate, not a silyl enol ether enolate. So you can see here the diastereoselectivity is nearly 90:10 with respect to the erythroisomer that is formed. The enantioselectivity of that particular isomer is 96. In other words, the erythro-trio ratio is 90:10 in this case. The erythroisomer, which is the major product, is formed in 96% enantioselectively because we are using a chiral derivative which induces a chiral induction during the course of the 3,3 sigmatropic rearrangement. The EE isomer produces a thrioisomer. You can explain the formation of the thrioisomer from the EE using a chair type of a cyclic transition state, which we have already seen in the earlier module. So use the same logic to draw the transition state, which is the chair type of a transition state, to go from EE to the trio and the ZE to the erythroisomer. The thrioisomer is also formed in very high diastereoselectivity. The trio-erythro ratio is 99:1, and after we get rid of the boron enolate to corresponding gamma delta unsaturated carboxylic acid, that carboxylic acid is produced in about 97% enantioselective manner. The major isomer, which is the thrioisomer, is formed in 97% enantio pure form of the isomer. The enantioselective synthesis of dolabellatrienone, which is this particular molecule, is a terpenoid molecule, is essentially obtained by the same strategy which is described in this particular slide. The boron enolate is stereoselectively synthesized first. The boron enolate that is generated undergoes the 3,3 sigmatropic rearrangement to produce this. This is transformed further into this terpenoid molecule by means of various transformations which are not relevant to the Claisen rearrangement. The first step is the Claisen rearrangement that is formed in about 96% diastereoselectivity is 96%. The major isomer is formed in an enantioselective manner to an extent of about 98% using the same boron enolate, which is this particular boron reagent being used to generate the boron enolate in this particular case also. Here is an example of the first generation asymmetric transformation of Claisen rearrangement. This is an alpha methyl benzyl alcohol. The alpha methyl benzyl alcohol, this particular isomer is taken and it is forming the corresponding enolate by treatment with this potassium dimethyl silicide in this particular case, and trimethylsilyl chloride captures the enolate that is formed in the form of ketene silyl acetal. The ketene silyl acetal undergoes the Ireland Claisen rearrangement in a stereoselective manner to generate this particular isomer, which is the erythroisomer in this particular case. The diastereoselect, after you get rid of the chiral auxiliary, which is this particular by means of hydrogenolysis reaction, because it is a benzyl ether, it can be cleaved by hydrogenolysis to produce the corresponding alcohol. The carbon oxygen bond is hydrogenolized to give the corresponding hydroxy derivative, alpha hydroxy derivative. This is obtained in a diastereoselective manner in this configuration to the extent of about 96%. The major isomer is formed in an enantioselective manner to an extent of about 50% of enantiomeric excess is what is formed in the major isomer of this molecule. Here is an example where the carbohydrate in the furanose form is used as a chiral auxiliary. The ketone, which is an alpha hydroxy ketone in this particular case, is undergoing addition of a vinyl Grignard reagent to produce the tertiary alcohol. The tertiary alcohol is captured in the form of a trichloroacetamidate kind of a derivative. The trichloroacetamidate derivative undergoes 3,3 sigmatropic rearrangement. It is more or less a Claisen rearrangement, except instead of a vinyl derivative, this is a iminol kind of a imine derivative is what is iminol kind of a derivative is what is formed in this particular case. Iminoether is the derivative that is formed in this particular case. The 3,3 system is that the carbon oxygen bond is broken and the nitrogen carbon bond is formed, which is the 3,3. This is 1, 2, 3. Similarly, it is 1, 2, 3. So the carbon nitrogen form essentially forms the corresponding acetam. This particular amine derivative is what is formed after the Claisen rearrangement. Now, cleavage of this particular carbon-carbon double bond to get rid of the chiral auxiliary essentially produces an amino acid, because this acetate can be cleaved to give the corresponding amine, and this carbon-carbon bond is cleaved to give the corresponding carboxylic acid. So this constitutes a synthesis of a optically pure amino acid, in this particular case alanine as the product, through a Claisen rearrangement of this type to give this derivative. The trichloroacetamidate is a very crucial intermediate which generates the system for the amino acid synthesis. It generates the tertiary, the secondary amine system. The secondary amine system is in the form of an acetate in this particular case, and that undergoes the cleavage of the trichloroacetamidate. Amide is what is formed here. The trichloroamide is hydrolyzed under acidic condition to give the primary amine, which is part of the alpha amino acid derivative obtained from ruthenium catalyzed oxidation of the carbon-carbon double bond in this case. Now, Enders have developed a methodology to use the S isomer as well as the R isomer of N-amino methoxymethyl proline derivative. The N-amino methoxymethyl proline derivative is essentially a hydrazine derivative. In the presence of a ketone, when it is reacted with the ketone, SAMP reacts with the SAMP S corresponds to the S isomer, R corresponds to ramp, R corresponds to the corresponding configuration of this particular chiral center. So the S isomer of proline is what is the derivative that is talking about. This is amino group that is here. Methoxyproline is what we are talking, methoxymethyl proline is what we are talking about as SAMP as the chiral auxiliary. The hydrazone that is formed has this particular structure with the configuration which is the enantiomerically pure configuration at this particular center. So this is an optically active compound. When the enolate is generated from this particular carbon here, and the enolate generated is essentially going to have a 3,3 sigmatropic character. The enolate that is generated, you consider this to be the enolate, then this would constitute a allyl vinyl ether kind of a derivative. You can see here the enolate to be the vinyl derivative. So the 3,3 sigmatropic rearrangement takes place between this carbon, which will be the enolic carbon, and this carbon, which will be the allylic terminal carbon. So 3,3 sigmatropic shift brings the isobutyl substituted carbon to this particular position, releasing this acid. That acid is reduced with lithium aluminum hydride to the corresponding alcohol. And after you get rid of the chiral auxiliary, you get the diastereomeric ratio to be 91%. The major diastereoisomer, which is shown here, is formed in about 96% enantiomeric excess. So the SAMP or the ramp is used as a chiral auxiliary, and the enolate that is generated will be chiral because of the chiral auxiliary in nature, and a stereoselective 3,3 sigmatropic rearrangement essentially produces these two chiral centers in a very diastereoselective as well as an enantioselective manner, which is reported in this particular work. The same strategy has been used for synthesis of this particular molecule, which is malingolide. Malingolide is this particular molecule which is synthesized by the same methodology. In this particular case, ramp is used as the chiral auxiliary. Here you see the stereochemistry is S, so it corresponds to SAMP. In this case, the stereochemistry is R, so it corresponds to ramp isomer. R configuration is what is reported in this particular case. The methoxymethyl proline derivative, which is forming the hydrazone with this ketone, and it's enolized. This alpha hydrogen to the ester is enolized in this particular case, and this 3,3 sigmatropic rearrangement produces a carboxylic acid. That carboxylic acid is reduced by lithium aluminum hydride. So there are two steps which are built in this particular scheme. The first step is the generation of the enolate, followed by 3,3 sigmatropic rearrangement to produce the carboxylic acid. The carboxylic acid is reduced with lithium aluminum hydride. So this hydroxy functional group is essentially coming from the carboxylic acid functional group which was originally present, which is being reduced by the lithium aluminum hydride. Subsequent hydrolysis of this molecule followed by transformation by means of Baeyer-Villiger oxidation essentially produces a necessary skeleton. Then the alpha alkylation at this position produces this methyl group, and further elaboration of this molecule into a long chain is what produces the malingolide synthesis in this particular case. Now here is an example of a chelation controlled chirality transfer of the Claisen rearrangement. What is seen here is the optically active amine derivative, which is a Bach protected amine derivative. This is used as the chiral center. Now when you produce a enolate by means of lithium hexamethyl disilocane, the enolate is generated here. That enolate will be now tied up by the titanium center. So in other words, titanium chelates between this oxygen and the enolate oxygen, forming a tight chelate, which is a well defined chelate. So as a result of that, the 3,3 sigmatropic rearrangement between these two centers proceeds very stereoselective manner to an extent of about 82% of diastereoselective manner to give this particular product. And the initial product that is formed will be a acid, carboxylic acid, because Ireland-Claisen rearrangement of this type will produce a carboxylic acid coming from this moiety, which is esterified into a methyl ester by treatment with the diazomethane. So this is an example. This oxygen here in the form of an enol and this oxygen here in the form of an amide is undergoing a chelation with the titanium. Titanium is acting as a metal template essentially to trigger this reaction to go in a diastereoselective manner in this particular case. There are several examples reported by Larry Overman, which are palladium catalyzed 3,3 sigmatropic rearrangement. The chiral palladium complex is what is used in this particular case. So the chirality of the palladium complex, essentially the chelation, the coordination of the palladium onto the oxygen essentially induces the chirality of the rearrangement itself. The 3,3 sigmatropic rearrangement of this particular derivative gives this tertiary amine, the tertiary amide in this particular case, in a highly enantioselective manner because of the chiral nature of the palladium catalyst that is used. So this is an example of an enantioselective immediate, this is the immediate amide, which is a product, immediate amide rearrangement, which is a 3,3 sigmatropic rearrangement in this particular case. Examples of asymmetric ESA and thioclaisen rearrangement are given here. This is an example of a asymmetric, first order asymmetric system, because this is a optically pure starting material is what is taken. Once you generate the enolate using LDA in toluene at a very low temperature, the enolate is highly reactive. So when it undergoes a 3,3 sigmatropic rearrangement at 120 degrees, it produces this particular diastereoisomer of the compound. So if X is equal to hydrogen, for example, this can undergo lactamization. Sorry, one second. This is when X is equal to hydroxy functional group, it can be made into a lactone. This hydroxy functional group is alpha position, which we are talking about. And this particular lactone is a natural product. Verucarinolactone is what the structure of this compound is. If you take this example, this is a nitro substituted thioamide is what is present here. Allylation using a base and allyl bromide will essentially generate the S-allyl derivative, because sulfur is a much more nucleophilic center, so S-alkylation takes place. So the deprotonation of the proton from this position results in the formation of a ene-thiol. The ene-thiol is trapped by this allyl bromide to generate the corresponding vinyl allyl sulfide derivative in this particular case. This undergoes Claisen 3,3 sigmatropic thioclaisen rearrangement at about 50 degrees Celsius to generate this corresponding center. Here, if the chiral auxiliary group is the proline group, which is shown here, then it is a proline template is acting as a chiral auxiliary group that induces the enantioselectivity of this particular compound. Because there is a chiral center here, the diastereoselectivity is what is reported for this compound to be about 66% in this particular instance. So what we have seen in this module is asymmetric Claisen rearrangement of aliphatic type, aromatic Claisen rearrangement, as well as the asymmetric version of aromatic Claisen rearrangement in the module. Hope you enjoyed the module. Thank you very much for your attention.